Planning and Economics section of the Nuclear Energy Department, Mr. Saeed Dardour, and he is a nuclear economics analyst, and he worked in the field of industrial simulation at Coris, France, C-O-R-Y-S, Coris. I'm not familiar, but most of you must be familiar with this. It's in France, before joining the Nuclear Reactors Studies Department of CEA. So he was leading the safety and design optimization studies related to Generation 4 reactors. So that's the background for him. And his lecture is in connection with the first one which we had in the morning from Loretta. So you try to connect it with the first lecture. And then we will have this presentation, I think, for about 45 minutes nearly. Then maybe followed by that there will be questions like we did in the morning. So now over to Saeed.
Thank you. Good afternoon, everybody. Welcome to this lecture on power generation costs. I think we will try to manage because I don't have control over the slides. Sorry for that, but we will try to manage. So the objective of this lecture is to get some insight on nuclear power costs and how these costs compare to costs attached to other forms of electricity generation. So we will be talking about costs in monetary terms, dollars and euros, etc., but also hidden costs, what we call externalities, social costs, which could be negative when we talk about green gas house emissions and pollution, for instance. And these costs could be, or these externalities can also be positive when we talk about macroeconomic impact. A nuclear project or program can have at the level of a country or of a region. So slide 4. So in slide 4, I'm just illustrating an energy system. So we have in an energy system, we have power plants from different technologies, and these plants are somehow connected. They are part of a grid. So they are not isolated. They are physically and economically interacting with each other. And each one of these plants is there for a purpose. And in general, when we talk about power production or investment in power production capabilities, we are looking for benefits such as security and reliability of supply, affordable prices for the consumer, global concern for climate change, and we are looking for a number of benefits which we expect from these power generating plants. Now, having all these plants in one place, in a grid, this is a bit challenging because
Hello, Saeed. Yeah, sorry, we are connected again. Yeah, but you switch on the microphone, please. Yeah, switch on your microphone. Yeah,
it's okay.
Yes, it's fine. Yeah.
So, as I said, these plants are part of a bigger grid, and what happens in one plant affects the other plants. So when we talk about costs, we have to keep this picture, in mind. Is that we are not talking only about the costs at the boundaries of the plant, but it extends beyond the boundary of the plants, and we can have costs related to the fact that the plant is a part of something bigger. So slide 5. So in slide 5, I just highlight the fact that in order to invest, and before investing in a power generation plant, we need to do what we call a demand and supply analysis. So this would justify the investment in power projects. And an equilibrium between supply and demand is also important for keeping the grid stable from the technological point of view, because electricity basically cannot be stored. Slide 6. So we have a tool here at the agency, and which was developed in the Planning Economics Studies section, which I'm part of. And this tool is called MAET, Model for Analysis of Energy Demand. And this tool can be used to describe current demand and to forecast future demand, which is a very good and important step towards taking a decision whether to invest on this technology or on that technology for power generation. Slide 7. So we have to forecast demand, but also we have to forecast supply, and many factors could affect the level of supply within a country. These factors could be the dynamics of energy prices. That could be some political decisions about the discontinuation of certain types of energy sources. In Europe, for instance, where in some countries, Switzerland, Germany, political decision had been made to phase out of nuclear. That would definitely affect the level of supply. The existing grid and its interconnection with grids from neighbor countries, that's also something that can affect the level of supply. Slide 8. Now we are talking about why we invest in energy projects. So we invest in energy project to achieve a number of objectives, like addressing an increase in demand in electricity in a given country, or to address some concern related to security of supply or mitigation of climate change. And to take the decision to invest or to not to invest, and to select the technology in which we will be investing, we need to do what I just talked about. It's supply-demand analysis. But we also need to do what we call an options analysis. So in order to achieve the same objectives, we have definitely different options. For instance, if we want to supply electricity to address a demand or an increase in demand, we can achieve the same objective by building a new plant or by improving existing plant, for instance, making them more efficient, introducing energy-saving technologies within that kind of plant. So we have options, and these options have to be compared. And this brings me to the content of slide 9. And this comparison is based on what we call a cost-benefit analysis. So this is a study that is conducted as part of any investment project to look at the costs and benefits of a power generation project compared to alternatives, possible alternatives achieving the same objectives, achieving the same project objectives. So slide 11. So now I'm going to talk about costs. So as I said, we are building power plants to address certain needs and to achieve certain objectives. And to do this, we will have to invest. And investing in a power plant means that costs will be incurred. So in this slide, I'm distinguishing three types of costs. We have plant level costs. These are basically the concrete and steel used to build the plant and the fuel and manpower to run it. We have grid level system costs, which are costs that are incurred at the level of the grid, the electricity distribution grid. And the third level is the external or social costs. These are the costs for which basically it's very difficult to put a monetary value on them. How can we put a monetary value on greenhouse gas emission, on air pollution? How could we quantify macroeconomic impacts, job, industrialization, development of research and innovation within a country? So all these are benefits for which it's not evident to put a monetary value on. So I will be discussing in the next part of my presentation these three types of costs. So slide 12. So I will be starting by plant level costs. So these are the costs at the boundaries of the plant, what we call the bus bar costs. So the bus bar is the item or the interface which connects the plant to the grid. So we stop there. And it's important to distinguish at this step between what we call dispatchable technology and non-dispatchable technology. So dispatchable technologies are technology for which the output can be varied to follow the demand. And this is typically, let's say, a gas turbine. If in a country we have, for some reason, an increase in demand because the weather is colder, or in summer because it's too hot, then we can just turn on a gas turbine and the demand will be fulfilled. Conversely, for non-dispatchable technologies, we don't have any control over the output of the plant. So these are basically variable renewable energies like solar and wind. As long as the wind blows and the sun shines, we will get electricity, but we will not be able to request additional amount of production from these energy sources. So we have no control over them. So this distinction is important for the second cost categories, which are grid level system costs. So slide 13. So this slide, or this figure in this slide, is from the OECD projected cost of electricity 2015. I shared this document with you. What it basically shows is how what we call the levelized cost of electricity varies dependent on the technology and dependent on what we call the discount rate. So we have this metric, an important metric for measuring costs, plant level costs, which is the levelized cost of electricity, or LCOE. LCOE is a metric that is very simple, pretty straightforward to use, and transparent, easy to calculate. Everybody can calculate an LCOE from a number of basic inputs. They capture plant level costs, but they don't capture external other costs beyond the level of the plant. What this figure shows is that this metric, the LCOE for nuclear is one of the lowest LCOE. So this is one conclusion. And the other conclusion is that the cost, the cost of generating electrical power from nuclear, as from other sources, but to a less extent, I think, this cost increases as we increase what we call a discount rate. So let me explain what is this discount rate. I won't be showing any slide. When we talk about cost, when you have a plant which produces a product, let's forget about electricity. Let's take a water plant. So you have costs. You have an amount of water that is purified by the plant. In order to calculate the cost of your plant, you divide all the expenditures you have by the volume of water your plant is treating, for example. And with this, you obtain a per unit cost in dollar per cubic meter. In the case of electricity, our plant is generating electricity, so it's generating megawatt hours, right? It's amount of energy. And to determine the amount of energy, a way of doing it is to take all the expenditure related to developing a power plant and to divide it by the volume of electricity generated over the lifetime of the plant. Now, the problem with this way of calculating things is that all the expenditures related to our plant are not incurred in the same time. So we have basically three phases. We have the reactor construction phase, for which a lot of effort is put in order to erect the plant. We have the reactor operation phase, or the electrical power plant operation phase, which can extend from 20 years typically for a gas turbine to about 60 years, and we talk even about 8 years for nuclear power plants. So this is the second phase, where we operate the plant and generate electricity. And the third phase, where, especially in the case of nuclear, we have to dismantle the plant and to manage the nuclear fuel waste, the waste, radioactive waste from reactor operation. So we have three phases. They span over something, period which is more or less a decade. And during all this period, we have expenditures that occur very near to the present during construction and in the far future regarding operation and dismantling. And as all of you know, time, there's a saying which say time is money. So the value of money depends on time. And $1 today is not worth $1 earned in 10 years or 20 years. So to have a common basis for comparing expenditures that are incurred at different moments in time, we use a concept that is called discounting. So we basically bring all future expenditures to the present, and then after discounting and bringing all these expenditures to the present, we divide all these expenditures by the total volume.
Hello, Science, yeah. We could hear you. Please switch on the microphone. Please switch on your microphone. Yeah? Okay.
Sorry for that. So LCUE is based on discounting future expenditures. This is the point. And for these expenditures are basically three categories: construction expenditures, operating and maintenance expenditures, plus fuel expenditures, and end-of-life expenditures. And all these are taken into account while calculating this metric, which is the LCOE. So slide 14. In slide 14, the LCOE values are provided for non-dispatchable technology. As I said a few minutes ago, we make a distinction between dispatchable technology, so nuclear compared to coal, compared to gas. This is the graph you saw on the last slide. And we distinguish this from non-dispatchable technologies, which are basically renewables. And this slide is about renewables. And in renewables, what we see is that, first of all, the LCOE is more or less in the same order of magnitude as dispatchable technology. And the second thing is that offshore wind is the lowest, is the technology achieving the lowest LCOE. So basically, at the level of a plant, power generation technologies, all power generation technologies have more or less the same cost. There are differences, but it's the same order of magnitude of costs. So now we move to what we call system costs. So slide 15, and we can go directly to slide 16. So, as I said in the beginning, a power plant is part of the system. So when computing cost, when summing up costs, we should add to the cost of building the plant, operating the plant, and dismantling the plant, we should add normally costs that are incurred within the grid. And these costs are of three types. The first type, or what we see in the top, are the costs related to the variability of output. So when we have a variable output from renewables, for instance, we need some backup capability. And this backup capability should be dispatchable when there's no wind or no sun. So this is what we call profile costs. We have balancing costs, and balancing costs are related to the fact that, again, when you have a system with increasing or with a high share of renewables, the variability of their output imposes on other plants, for instance, coal plants, to what we call ramping and cycling. So these are changes in the output of this plant to accommodate for changes in the output in renewable. When a coal plant operates not at its highest capacity, but at, let's say, 50%, these 50% for the coal plant owner or for the gas plant owner mean less electricity sold to the grid, so less revenue for him. And these are balancing costs. And finally, we have the third item, which is grid and connection costs. These are basically the costs related to investments in the grid, which are necessary for integrating, let's say, offshore wind turbines within the grid. When we install offshore wind turbines, we have to invest in power transmission system, and that has a cost. And that cost is not taken into account in what we call the plant level costs, which stop at the boundary of the plant. So slide 17. What we see is that due to increasing share and introduction of renewables, we have what we call these system effects, which translates into costs. And these effects are becoming increasingly important due to the fact that we have more and more power generated from variable resources. So, slide 18. So what is the impact of this increase in share of renewable on system costs? Well, there has been a study by the OECD, which also I shared with you, that shows that the system costs, the costs induced by the introduction of such technologies at the grid level, increases with the share of electricity generated by these renewables, which is not the case for dispatchable technology, which means that if we take two projects achieving with the same capacity of electricity production, we have offshore wind on one hand and let's say gas turbine on the other hand. So we put them on the grid. We have grid connection costs, we have balancing costs, we have profile costs. All these costs related to dispatchable technologies such as coal, gas, and nuclear are one order of magnitude lower than the ones attached to renewables. So now we will move to the third cost category, and I'm at slide 19. So the third cost category is probably the most difficult to quantify. So we moved from plant level costs to system costs and then to external or social costs. And by moving from one cost category to another, the difficulty to estimate costs and to put a monetary value increases. So slide 20. So we have basically two externalities which are common to all types of energy projects. So externalities, social costs, right? So we have, on one hand, the greenhouse gases emissions. So there was a report, I think, a few days ago, yesterday, or I don't know, a few hours ago, that was published on this, on the climate change challenge. So we have greenhouse gases, and we have air pollution. And there were a number of attempts to attach monetary value to these externalities. I'm providing a few links here in this slide, but I won't develop this in detail. Slide 21. What is important to know at this step is that when we evaluate costs, be it plant level costs or external costs, we consider the life cycle, the total life cycle of the plant. So, for instance, for nuclear and for greenhouse gas emissions, for CO2 emissions, this is slide 22, we consider the emissions from mining of uranium to all the front-end aspects, fabrication of enrichment, fabrication of fuel, etc., to the final decommissioning of the plant and management of radioactive waste. So all these periods is taken into account when estimating what we call a lifetime cost. So this is a life cycle analysis, which is used as a basis to quantify the volume of pollutants or CO2, which is emitted per kilowatt hour of electricity produced. And this is the reason why, for instance, nuclear or renewables are not totally carbon free. There is a small amount of emissions which is associated with, for instance, in nuclear, with enrichment. In France, for example, there was using gaseous diffusion as a process for enrichment, which consumes a lot of energy, and part of that energy comes from fossil fuel type of sources, of energy sources, and that's taken into account. So life cycle assessment, this is the basis for estimating the emissions of CO2 and pollutants per unit of electricity generated. Slide 23. So in this graph, we have the life cycle emissions associated with each technology for power generation. What we can see in the bottom is that nuclear is one of the lowest producing CO2 producing technologies on a life cycle basis. And with nuclear, we have also hydroelectricity, wind power, and solar, which also produce a low level of greenhouse gases per kilowatt hour of generation. On the other hand, we see that emissions are substantially higher for fossil technologies. Slide 24. So basically, nuclear is one of the energy sources that emits the lowest volumes of CO2 and pollutants. But when nuclear power was initiated, let's say at the middle of the last century, this was not the objective of developing nuclear or hydropower. The objective was probably to respond to some geopolitical events, like the case in France. France decided to initiate its nuclear program after the oil crisis in the 70s. Or to secure the supply of energy. Now the situation has changed in the last few years because of concerns about air pollution and climate change. But initially, this was not really the rationale behind developing nuclear power and, to a less extent, renewables. So what happened is that thanks to nuclear, thanks to hydropower, a lot of emissions have been avoided during this period. And if we look at slide 25, we have on the right, we have the gigatons of avoided emissions which were achieved thanks to carbon-free technologies. And this, sorry.
Sorry, Syed. Yeah. Okay. Please switch on the microphone. Yeah.
Sorry. So nuclear power, along with other renewable sources of energy, have been contributing to reducing the emissions, CO2 emission, and to mitigating climate change in the past. And that role is likely to continue in the future. But this basically depends on the scenario. So slide 26, how nuclear and how the share of nuclear is going to evolve, how demand for electricity is going to evolve. So this will impact and influence how nuclear could be used for mitigating climate change effects. So slide 27. So slide 27 is from the Climate Change and Nuclear Power Report the agency has produced this year. And what this slide shows is that the agency estimate for nuclear power are decreasing. So compared to a report published last year, estimates for nuclear power generation capacity and its share in electricity production is likely to decrease by 126 gigawatts in 2050, and that means some 12 gigatons of CO2 equivalent emissions that will be emitted and for which nuclear cannot reduce this type of emission. And if the objective of to reduce this emission, which are associated with a decrease in role of nuclear power, if we want to achieve this objective thanks to renewables, we have to invest something like 1 trillion in renewable energy in order to achieve the same objective of reducing these 12 gigatons of CO2 equivalent. So to summarize, nuclear power has been contributing to CO2 emissions in the past, but the future is uncertain as it depends on how nuclear and nuclear capacity will be added in the next decades. So slide 28. So in slide 28, I'm referring and I'm talking about another externalities, which is more or less related to CO2 emission, which is air pollution. So what the World Health Organization says is that 9 out of 10 people breathe contaminated air, and that results in a number of deaths, up to 7 million people per year, caused by air pollution, either outdoor or indoor. In the table, in this slide, we have so there was an effort to put a monetary value on this. So it was not, it's a complex process. It's not easy, but still, the OECD has done a study and attempted to put a monetary value on the pollution, on air pollution. And basically what this table shows is that the nuclear fuels, the nuclear and photovoltaics have less emissions of pollutants compared to coal and gas. But this is unfortunately not taken into account. This is not internalized in plant level costs. So I'm moving to slide 13. So I presented plant level costs, I presented grid costs, and I presented the costs in terms of CO2 emissions and emission of pollutants. With these costs, we have also benefits. And now I'm going to cover the part of the presentation that focuses on the benefits of nuclear power and how these benefits vary from one technology versus another. In slide 13, I'm just reminding you of the rationale, the economic rationale behind energy investment projects. So we invest in power plant basically to increase and diversify the energy supply, to increase the security of supply. We may want to increase the efficiency of power conversion. So this is slide 31. Or we may want to achieve a better market integration that would result in a decrease in price for the consumer. Slide 32. So let's take one of them. Let's take the security of supply. So what is the security of supply? Basically, it's the reliability of power generation and the ability of power generation system to supply electricity to a grid without, with minimum, I would say, shutdowns and unavailability of the power source. The OECD has done a study to quantify how, or to see how the security of supply improved in OECD countries from the 70s of the last century. And what this study shows is that thanks to the introduction of nuclear, the security of supply, which was measured by an index here, which is called the SSDI, has been improving in countries, more in countries that relied on nuclear power than in other countries. So slide 33. So this is one benefit of power generation project to which nuclear power is clearly a key contributor. The other benefit of nuclear program is related to the impact a nuclear project or program can have on a country. So here I'm in slide 33. Sorry. So what we know from economic studies from the European Commission, for instance, is that, or the World Bank, is that when a country invests and invests heavily in infrastructure projects, big infrastructure projects, such as power plants, transport network, etc., it is very likely that these investments, multi-billion-dollar investment, induce some macroeconomic benefits within the country. And if we take a country, so maybe you can move to slide 34. So this is from the Hinkley Point C project in the UK. So, yeah, it's nuclear project. Nuclear project is a big project. It has nothing to do with a combined cycle or a solar panel field project. This is a huge project. It's a multi-billion project with a lot of investments made, with a lot of workers, a lot of local enterprises, contractors supporting the project. So an economic dynamic at the regional level, maybe at the country level, that has no equivalent in other forms of power generation projects. And slide 35, when a country decides to build a nuclear power plant, there's actually many components which could be supplied locally, fabricated locally. So on the left-hand side of the slide, I'm just enumerating some numbers regarding the components, typical number of components a nuclear power plant have. And as you can see, so we have huge quantities and volumes, and many of these can be, these components, the services related to construction, can be supplied locally. For instance, concrete can be supplied locally, structured steel can be supplied locally, cables, etc. There's a huge potential for the local industry to be involved in such a project. And that's a huge benefit, an economic benefit for the local economy. Slide 36. An additional benefit is related to nuclear is the fact that nuclear is a labor-intensive and it's much more labor-intensive than compared to other forms of electricity generation. And if we take on a per megawatt hour of generated electricity, nuclear requires more jobs, more manpower with higher qualification over longer periods of time. And this employment, highly qualified employment in big numbers and over long periods of time is a form of positive externality of nuclear power. So in the left-hand side, I'm just putting some numbers to describe the number of people working on a plant, on a reactor construction site. I think in the UK we have something like 3,000, but it can go up to 6,000 workers working on the reactor site. Slide 37. So in this slide, so this slide is from the real case, which shows how macroeconomic benefits, increases in production output, increases in output, plant outputs, increase in turnover for the businesses, different businesses within a country, how these are distributed across the different sectors of an economy. So I have basically two graphs, one in slide 37 and the other in the next slide. The first graph, slide 37, shows the sectors that benefit most from a nuclear project in the supplier country, in the country that supplies the nuclear technology. And about 25% of the total output increase is within the businesses that manufacture machinery and equipment. If we look at the country that is recipient of the nuclear technology, this is slide 38, we have also an important economic So slide 38 shows that the impact of a nuclear project can have on the country that receives or in which a nuclear power plant is being built. In this country, two sectors account for almost half of the total output increases, which are construction and manufacture of machinery and equipment. So I'm at the end of my lecture. We can move to slide. Let's move to slide 42. So these are the main key takeaways from this lecture. The first takeaway is that power projects, nuclear and non-nuclear, all power projects have an economic impact, but also a social and environmental impact. So the difficulty is to quantify the impacts in monetary terms. So this is the first takeaway. The second takeaway is that in many countries, the demand for energy is growing. And at the same time, there's a concern about climate change and health, public health. And to meet or to address these kind of questions, energy technologies, novel energy technologies that are carbon-free are needed. But these technologies are not valued as it should be today. So when estimating the cost and benefits attached to these technologies, externalities are not fully taken into account. And this should change. And air pollution, climate change, system costs, macroeconomic impacts, all these should somehow be taken into account and add to the plant level costs I showed earlier. So nuclear has significantly contributed to greenhouse gas emission mitigation, but it must accelerate growth in order to meet the objectives of the Paris Agreement, for instance. So that's the end of my presentation. I have I have some annexes on plant level costs and cost drivers if you are interested, but please feel free to ask your question. Thank you.
Thank you, Saeed, and